Yeah, you can start.
Okay. Okay, good evening to all of you and welcome to this Indian Physics Association Colloquium. And we welcome you from the Department of Physics and Chandigarh chapter of IPA and through Indian Physics Association. And today's speaker is Professor Srikant Sastry. And Professor Srikant Sastry, actually he's a full professor at JNCSR. And Professor Sastry obtained his PhD from Boston University in 1993. And he has a few postdoctoral research fellow at National Institute of Health and Princeton University. And he joined JNCSR in 1998. Now he's a full professor. And his specialty is in nonlinear physics, and particularly in statistical physics and disordered systems. And he has done quite a lot of work in these fields. And today he will talk about the Nobel Prize in Physics in 2021. You know, this year Nobel Prize was shared by the three people. On the physics side, it was by Giorgio Parisi, who talks about the spin glasses and other things. So Professor Sastry today will talk about the decoding complexity, Giorgio Parisi, and the theory of spin glasses and beyond. So he will start his talk now, and we'll here the speakers are both in the Zooms and also YouTube. So at the end of the talk, we'll take you can write your questions in the chat box. At the end of each talk, we'll take it first from the Zoom, then from the YouTube. So now invite Professor Sastry to deliver his talk.
Yeah, thank you. Thank you for this invitation. I'm very pleased to be talking about the work of Giorgio Parisi, who I've known for a couple of decades and admire greatly. I'm very happy that his work has been recognized in this way. Okay, so what I want to start with is sort of a broad description of what kind of work has been awarded the Nobel Prize this year. I will say a little bit, but not nearly enough, about the first half of the Nobel Prize that was given to Soichiro Manabe and Klaus Hasselmann. But mostly I'll talk about Giorgio Parisi. So here is a snapshot of the Nobel webpage, which says that the awardees this year have been recognized for groundbreaking contributions in our understanding of complex physical systems. And the citation for Manabe and Hasselmann says, for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming, and for Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Okay, so there's some keywords that are in these citations: complex physical systems, modeling the Earth's climate, quantifying variability, global warming, disorder, fluctuations. These words or keywords represent a new paradigm of comprehending the world that has emerged in the second half of the 20th century, which goes under the name of complexity. And I hope to convey some sense of what that's about. Now, these are physics Nobel laureates. How does it fit into the grand scheme of what physics tries to do? So we all understand physics as a branch of science where the focus is on the search for universal laws, fundamental constituents, and forces, and conventional physical phenomena that we study are characterized by words such as equilibrium, ordered, linear, ergodic. And I'm sure there are more keywords that one could use to describe what conventional physics is about. And typical characteristics of either physical theories or phenomena that are described by successful physical theories are predictability, regularity, order, etc. And I mentioned these particular characterizations to say that complex phenomena, on the other hand, are characterized by several negations of these attributes. So non-linear, non-ordered or disordered, non-ergodic, non-equilibrium, etc. And the distinct character of phenomena in this class were increasingly appreciated in the second half of the 20th century and were guided by the exploration of some major themes of research. I mentioned a few examples. One is the study of nonlinear dynamics, chaos, etc. And the other is the exploration of non-regular geometries that arise fundamentally in physical sciences, fractal geometry, and the study of disordered physical disorder, the role of disorder in physical systems. And this is just to sort of give a flavor of what complex phenomena typically tend to involve. These are all interconnected themes. In the interest of time, I won't try to sort of expound on that further, but let me start by sort of like poster boy of complex phenomena, which is turbulent flows. And this is something that we experience every day. When you turn on the kitchen tap, if you turn on the tap by a small amount, you have regular lamellar flow. But if you turn on the tap more, you have turbulent flows, as shown in these pictures here. And there are, of course, a lot of fascinating and interesting examples. And over several decades, since this phenomenon has been studied, people have sort of really appreciated the special character of this phenomenon. Here are a couple of quotes by eminent scientists. Let me just read out the one by Werner Heisenberg, who's supposed to have said, when I meet God, I'm going to ask him two questions: why relativity and why turbulence? And he says, I really believe he'll have an answer for the first, okay? Now, this kind of motion or dynamics is sort of part of nonlinear dynamics and chaos, which has been explored a lot in the last few decades. So dynamical systems are systems of equations that describe the dynamics of a physical system with several degrees of freedom. And the presence of nonlinearities in these equations of motion lead to deterministic but seemingly very irregular or chaotic motion. One of the simplest examples is the double pendulum, which is shown here in the video, and one must contrast it with the behavior of a simple pendulum, which is very regular. And one of the things that is characteristic of chaotic motion is something called the sensitivity to initial conditions. And this is illustrated in both this sort of very nice experiment where apparently starting from the same initial conditions, these double pendula over time end up being in very different positions at a given time. And at the bottom right, you have the time trace of some variable in a nonlinear system, which again starts out with very initial conditions which are very close. And but after some elapse time, the values of this variable become very, very different. Okay, and this is something that has been characterized as the butterfly effect, and described through this colorful example or hypothetical example that a butterfly flapping wings in Brazil can cause a tornado in Texas. And the weather connection or the illustration is not accidental. Some of the early work were nonlinear dynamics and sensitivity to initial conditions. Excuse me. was explored was in attempts to model the weather, most notably Edward Lorenz, who discovered this phenomenon of sensitivity to initial conditions in the model of weather that he was working with. And now this realization appears to be very bad news for weather prediction. So how can we reliably make statements about weather or climate despite the presence of the sensitivity? And in the context of this year's Nobel Prize, one must distinguish climate and climate change from weather. So the basic idea is that what we call weather, which is, whether it's going to rain tomorrow, if it's going to be sunny, is sort of representative of a fast component that is associated with something that's more systematic and regular, which we call the climate. And it is indeed possible to model and investigate climate change more reliably or with greater robustness than weather. And this is a work that was pioneered by Hasselmann. And the idea that, in fact, you can actually represent the weather through a dynamical system with a small number of degrees of freedom that incorporates things like interaction of radiation and mass transfer, the role of carbon dioxide, etc., is something that was pioneered by Manabe, for which they've been recognized with the Nobel Prize this year. And okay, that brings me to the major theme of what I'm going to talk about, which is investigating disordered systems. And first, let me say a few words about disorder. When one looks at physical systems, thermodynamic systems, of course, disorder is something that we're all very familiar with as being part of all the things that we see around us. And this is the disorder that arises from thermal motion, okay? And this is quantified by the entropy, which quantifies the multiplicity of microscopic states a substance can explore on the time scales of making a measurement. Thermodynamics and statistical mechanics tell us that a substance will reside in states that minimize the free energy. And the free energy is the internal energy of the system minus temperature times the entropy. Now, in spite of the incorporation of disorder due to thermal motion, the resulting behavior can indeed be very orderly, leading to smooth variation of properties, such as a simple-minded example, the ideal gas law, which says that the pressure increases if the temperature increases, right? And we generally have the situation that at low temperatures, the properties of a thermodynamic system is dominated by energy, and entropy sort of dominates the behavior at high temperatures. So this is sort of like the more familiar notion of disorder, but not all forms of disorder are the same. And in fact, for today's talk, the disorder that we are concerned with is the disorder in how atoms, molecules, spins, etc., interact with each other that leads to complex behavior, and in particular, glossy behavior, okay? So with that, let me come to Giorgio Parisi, who's the recipient of the other half of the Nobel Prize. And he has been recognized for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. So Parisi is a versatile theoretical physicist whose seminal contributions encompass particle physics, several aspects of complex phenomena, including spin glasses, computer simulations of complex systems, etc., including climate change modeling, turbulence, etc., and enumerating in moderate detail all of these contributions can easily fill a lecture. But what I would like to do today is actually to take some strands of his work rather than spend time praising him. I would like to try and explain sort of the key work for which he's well recognized. And this is the theory of spin glass and glass transitions. And if time permits, at the end, I will say a little bit about some of the ramifications which you would expect any important work to have. And certainly the work in Parisi's work in spin glasses has had very interesting ramifications in diverse areas. Okay, so let me begin by just sort of setting the terminology for those who may either be unfamiliar or rusty on these things. And you know, these are things that most physics students and chemistry students will be familiar with. But I don't want to jump into spin glasses right away and lose my audience. So very simple things. If you look at, again, a thermodynamic system, if I ask what's the probability of being in a certain state, certain energy, or occupying states with a certain energy, it's given by two terms. One is this G of E here. By the way, do you see my cursor? Dr. Baira?
I can't see it.
No, okay. Right, I'm not going to try and do anything about it, but I'll just sort of say in words, okay? And G of E is sort of the multiplicity of microstates at a given energy, and then you have the Boltzmann weight exponential minus E divided by KT, where E is the energy, and this we can rewrite by defining this quantity called S, which is the logarithm of G of E, as exponential minus E minus Ts divided by KT. And this you recognize looks like the free energy that I already mentioned. And so the probability of occupation of a given energy is given by the exponential of a microscopic free energy, if you will, divided by kBT. Okay. Now, one in statistical mechanics works with something called the partition function, which is the sum over all energies of this probability. And this is equal to more properly the exponential of minus the free energy divided by kBT. And so in this row of schematics here, I display how the Boltzmann weight varies as a function of the energy, which is, it becomes smaller and smaller as you go to high energies. On the other hand, the multiplicity of states becomes bigger and bigger, and the competition between these two picks out some particular value of the energy as the most probable. And equivalently, we can say, if one sort of talks about if one writes down the free energy, this free energy is a minimum at the most probable energy. And this is what characterizes an equilibrium state, a free energy minimum. And here it's sort of drawn with respect to energy, but one typically also does look at free energy functions with respect to different order parameters. I'm giving you this introduction because when I come to spin glasses, all of this should be straightforward. Okay. Now, the next thing, that's just sort of describing equilibrium behavior. But the next thing we want to talk about is phase transitions, and a familiar phase transition that is a good starting point is the boiling of a liquid when temperature is increased. And this is something that's very well understood. And a lot of the understanding that we have has been gained by looking at very simple models that capture the universal behavior. One such model is called the lattice gas, where you imagine that you divide up space into little cells, as shown in the middle schematic, and you say each cell is either occupied by a particle or not occupied. And this description can equally well be translated to talking about spins at each of these cells, which are up if a cell is occupied or down if a cell is not occupied, because what we're dealing with are binary variables. And the corresponding model is called the Icing Model. And this is a simplified model for a magnet that undergoes a transition from a paramagnetic state where the magnetization is 0 to a ferromagnetic state when temperature is lowered. Okay, and the energy for such a system, and from now on I'll not talk about the lattice gas. I just wanted to make the connection between boiling to the Icing model through the lattice gas as an intermediary. So the energy of these spins that interact with each other and may lead to ferromagnetic behavior can be written as a sum over pairs of spins that interact with a certain strength, Jij, times the state of the spin, SI/Sj. So if you say that in the ferromagnetic case, if two spins are parallel to each other, the energy is lowered. Likewise, if the spin is parallel to an applied magnetic field, which is represented by small h here, then the energy is lowered. And the resulting behavior of interest is the behavior of the magnetization, the sum of the values of all of these spins. Okay, and as I already said, in the Icing model or equivalent simplified models, the spin is either +1 or -1. And the magnetization, which represents how these spins are ordered, is called an order parameter. And if all the spins are all +1 or all the spins are all -1, you get the magnetization to be +1 or -1 as well. And it describes the nature of the ordering in the system. Okay, and at low temperatures, of course, energy that I've written here favors that all spins are oriented parallelly. Going forward, I'm going to ignore this second term in the energy function, which corresponds to the effect of the applied magnetic field. We're just going to set that to 0. Okay, now the magnetization that I have written is an equilibrium property. That is, I average over all possible microscopic configurations, and I can equally well write it as a sum over equilibrium averages of individual spins. Okay, and I'm going to represent this by small mi. And all of what I'm saying in the last few minutes sounds like excessive detail of elementary stuff, but I'm doing it with a purpose, because when I come to spin glasses, all of these things will be useful. Okay, now I already talked about free energies, and here is now drawing two instances of how the free energy looks as a function of the magnetization. Okay, at high temperatures, this free energy curve has a single minimum, but when I go through a temperature called the critical temperature, or TC, to lower values, this free energy curve develops two minima at some value plus or minus m, and this signals a phase transition to the ferromagnetic state, and now there are two minima which are characterized by, on average, the spins being in the up direction or in the down direction, and these are equivalent because the magnetic field has been set to 0, and this is called spontaneous symmetry breaking for okay, we'll say without saying more. But the main point is, if I now look at a physical system, a magnet, and I lower the temperature below TC, I will end up with one of these two minima, and the system stays there forever, because the barrier to cross in order to go to the other state is very high. Okay, therefore, even though my free energy curve is symmetric, and it doesn't favor either the plus state or the minus state, in an actual experiment, if I lower the temperature, I'll end up with one or the other, and then I'll stay there. Okay, Now, consider an experiment, and this is important. It's simple, but it's important for later, where I keep raising the temperature to values above the critical temperature, and I lower it to some value below the critical temperature. And I keep doing this repeatedly, right? I do this many times, and each time I let the system equilibrate, and I ask, what is the magnetization? And I make a table of this, okay? Now, equivalently, I can imagine that somehow I'm able to make multiple copies, independent copies of the system or replicas, and I ask, what is the magnetization for each of the replicas, okay? Now, if I take all of these magnetizations for each of the replicas, and I average over them, I'll get 0, because I'll randomly be going into the plus or the minus state, and this will not reveal the presence of the phase transition, okay? But the histogram of the magnetization values will be bimodal, and that fact will reveal that there is indeed a phase transition. Now, I can do something a little bit more complicated, right? Which is, I look at the state of the system in each of these replicas, right? And I define something called the overlap function, which is the sum over all the spins, and inside the summation, I have the magnetization of each particular spin on average in the two replicas A and B. Okay, this is sort of, if I didn't look at the equilibrium magnetization M, but an instantaneous magnetization value, or the spin value, which is +1 or -1, you have the situation depicted on the right-hand side. So if I consider two spin configurations, A and B as shown, there are some locations where the spin values are the same, and the other locations where they're different. So then I get sort of an overlap values of +1 or -1 at each site. And if I average all of this, I get the total overlap. I mean, this is just a way of comparing two images, if you will. Now, if instead of looking at SI at each state, the spin values at each state, instead of that, I consider the magnetization value at each state, equilibrium averaged, then I have basically two values for this overlap, right? It's either +m² or -m², because the system on average is staying at +m or -m. And if I only bother about the magnitude, there's only one value, which is m². Okay. Again, I do this experiment of repeatedly generating different replicas, and now I calculate the overlap between the magnetization states of the different replicas, and this I'm going to call Q for simplicity, without worrying about the labels A and B. And now I can make a histogram of these overlaps, and this I'm going to call P of Q. And this histogram is shown at the bottom right, which basically has two delta functions at -m² and +m². Okay. Now, instead of having just one peak at Q equal to 0, which would be the case for the paramagnetic state. Okay. Now, this is sort of a very complicated way of describing magnetic order in a model of a ferromagnet. Okay. It's not really necessary to do it this way, but this overlap function P of Q turns out to be essential when we talk about spin glasses. Okay, so let's talk about spin glasses. These are basically, in terms of actual materials, spin glasses are solids with magnetic impurities, metals with magnetic impurities, which are at random locations. And it turns out that when you have if two magnetic impurities at a certain distance, the interaction between the magnetic moments and the electrons induces an effective interaction between them called the RKKY interaction. And these interactions have a particular feature, which is that they have an oscillatory component. which means depending on what distance that I am apart, or the two magnetic impurities are apart, the interactions can be positive or negative. And this is a new feature compared to what we talked about so far. And so we have what are called ferromagnetic when the interaction J is positive, or antiferromagnetic when it is negative. Now, this has a fundamental consequence. So if I illustrate that here with this triangle that is shown in the middle of the slide, where I consider 3 spins, and 2 of those spins, or 2 of the pairs of the spins, have ferromagnetic interactions, and the third pair has antiferromagnetic interactions. And now I ask the question, what is the optimal configuration of spins so that the energy is as low as it can be? Now, if I had all ferromagnetic interactions, the answer is obvious. They should all be pointing parallel to each other, and that's the lowest energy configuration. But when you have both ferromagnetic and paramagnetic interactions, the 2 ferromagnetic interactions want the spins to be, the 3 spins to be parallel, but the antiferromagnetic interaction wants 2 of those spins to be antiparallel. And both of these requirements cannot be satisfied simultaneously. And this leads to what's called frustration, which is a technical term. So then the question is, what do you expect? So if I have a system where spins are at random distances from each other, and therefore their interactions can either be positive or negative, what happens as compared to ferromagnet, right? So does the phase transition simply go away, or whether there's going to be a phase transition to some ordered phase despite the disorder, or something new happens? So that's the question. Now, what happens experimentally is that there is, in fact, a continuous transition, and this is signaled by, for example, a cusp-like singularity in the magnetic susceptibility. I won't say more about it, but because it's a disordered system, because there is frustration, you do not find any magnetic order like the ferromagnets. But there is some indication that at low temperature, the magnetic moments individually become frozen. So the question then is, what is happening? What is the nature of this transition? Okay. And the other feature, which I will not say more about, is there is a lot of very complex and slow dynamics in these spin glass systems. Okay. So how do we understand this? And based on what I said, we can say, let's take the energy function or Hamiltonian that we already wrote of Ising spins, but now the interaction strengths, instead of all being positive, the Jijs being all positive, some of them can be positive and some of them can be negative. And in the simplest model that has been extensively studied, in particular by Parisi, you take these interactions to be finite between all pairs of spins. So this is called a mean field or infinite range model. Okay, so how does this describe the spin glass behavior? Now, when you have an energy function where each pair of spins has a coupling which is a random variable, which it can be positive or negative, something, over some continuous range, then you have a system whose each microscopic state is described by an infinite number of variables. Okay, I mean, if the system infinite, as in if the number of spins is very large, the number of interaction strengths is also equally large, or larger actually. And this doesn't make sense. We are used to dealing with thermodynamic systems where we describe the properties of the system in terms of 1 or 2 parameters, temperature, field, etc. We don't want to describe the properties of the system with a huge number of variables, right? So the question then is, how do you deal with the disorder that is implicit in the interactions? And the physical sort of intuition is, if I have one particular piece of spin glass which has a certain set of frozen Jij values, it won't behave very differently if that same material had another realization of this disorder. Okay, so the important thing is that these interactions are disordered and they're frozen, they're fixed. So what you can say is, well, I can then find a way of averaging over this disorder realizations, and that should give me a description of the system that is meaningful. But it's important that what you have to average is the free energy and not the partition function. This is the reason why I introduced these partition function and free energy earlier. So based on what I wrote earlier, the free energy is the logarithm of the partition function, and it's that logarithm that you have to average over the disorder. Okay, how do you do this? And this is difficult technically, but what people did is to say, let's use this simple-minded expression for the logarithm of a quantity x or z, where if I look at z to the power n, I can write it as exponential n log z, which I can expand. And now if I take z to the n minus 1 divided by n and take the limit n goes to 0, that gives me the logarithm. Okay, therefore, if I want to average over disorder logarithm of z, I take z to the n and I average it over the disorder. Okay, now what is the value of n? Eventually, I want to take this limit n equal to 0, but right now I'm going to leave it as some unspecified integer value. Okay, now if I have z to the n, this is the partition function of n copies or replicas of the same system. Okay, so this is what one did, and this is called the replica trick. And we won't worry about the physical meaning of it just yet. First, we will ask, how does one calculate with this? And but the important thing to note here is you translate the problem of calculating a disordered average free energy into calculating a disordered average partition function over n replicas. Okay, so this brings us to the Parisi solution of this problem. In order to sort of think about how Parisi and others approach this problem, it turns out the key quantity is the overlap matrix, which we already introduced. Since we have n copies of the system that we are calculating the partition function of, without stretching your imagination too much, you can appreciate that somehow in the calculation, the overlap between these different replicas enters the picture. So you have this matrix of overlaps QAB, and then you have to figure out how you're going to solve the problem in terms of this overlap matrix. And the simplest thing one can think of doing is what's called a replica symmetric solution, which is you treat all pairs of replicas as having the same overlap. Okay, and this allows one to solve the problem, calculate the free energy averaged over the disorder, but it turns out to be not meaningful. You, for example, get negative entropies at low temperatures, and this is not okay, right? So therefore, you have to do something else. And this is where Parisi's insight came into the picture. What Parisi envisaged was that the physical solution for the problem would not have this symmetry between the replicas. Each of the replicas is not the same. The relationship between them is not the same. So this, the overlap matrix would have a very non-trivial structure. So if you look at the blue boxes at the bottom, the replica symmetric solution is when all pairs of replicas have the same overlap. But Parisi proposed a hierarchical scheme where first you sort of group these replicas into subsets, and you say that if you're within the subset, you have a given value of overlap. But if you're not in the same subset, then you have a different value of the overlap. And this procedure you can recursively apply to smaller and smaller subsets. And so then you can easily imagine that you end up with a whole range of overlap values between different pairs of replicas. And so Parisi's proposal was that you have what is called a continuous replica symmetry breaking, a continuous range of possible overlaps between replicas. And this is what characterizes the spin glass phase. Okay, so this is a very unsuspected, strange, and beautiful result. So through this scheme of defining these recursive sort of sub-blocks of the overlap matrix, you end up getting an overlap function P of Q, which I introduced already, which looks now very different from the ferromagnetic case, where it has finite value over a whole range of Q values. Okay, and this maximum value defines sort of the degree of order or describes the order that is present in the spin glass phase. And that order parameter, like the magnetization in a ferromagnetic case, increases continuously below Tc, the critical temperature. Okay. Now, okay, that's just a statement of what was done. It's not at all clear what it means. So here is one sort of additional property that Parisi and co-workers figured out, which is something very, again, quite unexpected in some sense, which is, instead of looking at a pair of replicas, if I now ask, what is the relationship? What is the overlap between the three possible pairs of replicas? If I pick three of them randomly, it turns out that they have a very special property, which is two of the overlaps always end up being the same, and their value is smaller than the third overlap. Okay, so this is sort of like picking three people and asking how closely are you related, right? And you always find this answer that two pairs of people are distantly related, and the third are closely related. Okay. Now, this is a property of a genealogical tree structure or a hierarchical tree structure, where how closely you're related depends on who is your common ancestor in the genealogical tree. Okay. And this is a remarkably regular structure of the organization of states in what we started out as being a very disordered system. Okay, so this is one of the remarkable features of the spin glass solution that Parisi found. And okay, now what does this all mean? Because people introduce the replica trick as a trick to solve the free energy of a disordered system, and then we're talking about this very special organization of these states. What does it mean? The physical picture, I won't elaborate too much, but by now I think it's clear. The physical picture is, when you look at the spin glass state, it is characterized by the presence of not a unique free energy minimum, but a whole lot of them. And one can think of these as representing what is called these days a rugged free energy landscape. And this free energy landscape will have many minima, and they are related in some specific ways. And this is a physical picture that one has of a lot of different complex materials and systems, such as, of course, spin glasses, but also molecular or structural glasses, biomolecules, and more generally, one can think of problems in evolutionary biology, fitness landscapes, and as I'll say in a minute, optimization functions, etc. in computer science, and the special place of the Parisi solution in this new view of how one might think about complex materials and systems is that it's a paradigm problem where there are some very concrete and detailed answers about what is the nature of the spin glass phase. Okay, so that's the contribution that's of significance. Now, that's okay. So far I talked about one particular model of a spin glass, which is where pairs of spins interact with random interaction strengths. But one can and one has considered different types of spin glasses. And one particular model is called the p-spin model, where instead of pairs of spins, you take groups of p spins, where p can be greater than or equal to 3, and write an energy that again has an interaction strength for each group of p spins, which is random. And it turns out that this model also shows a phase transition, but of a different character. It shows a phase transition where instead of the order parameter Q max that I introduced earlier, the maximum overlap, that instead of increasing smoothly, continuously below TC, it shows a jump to a finite value. So this is a first order transition. And of course, this is a first order transition in a random or a disordered system. So this is called a random first order transition. Okay. Now, one key feature that you may be familiar with in first order transition is that on either side of this of a first order transition, such as a liquid boiling or freezing, is that you have metastable states. So if you take water and cool it below 0 degrees, sometimes you can stay in the liquid state even at temperatures where the equilibrium state is a crystal. And so this first order transition also has metastable states. And so if I come from below the transition to above the transition, there is a persistence of these metastable states. Okay. And the difference between the example of water freezing into ice is that the number of these metastable states that persist above TC is exponentially large, which means that I can define an entropy that is associated with how many of these metastable states exist. And there's a picture of the dynamics that might take place in the system where the presence of all of these different metastable states and transitions between them will lead to very non-trivial and interesting dynamics. And there's also another feature that is of interest, which is if I look at this so-called complexity, which is the entropy associated with these metastable states, it starts out being finite and goes continuously to 0 at the transition temperature. Okay, so this is an entropy vanishing transition. And one striking feature of all this is it has strong resonance with how people have been thinking about the glass transition in supercooled liquids, where there is something called the Kaufman temperature, which is an entropy vanishing transition. There is something that people call configurational entropy, which is a measure of how many distinct sort of states you have, liquid states. And so this model actually turns out to be very close in character to how people think about structural classes. And I won't go through the characterization of this, but basically when you cool a liquid down, you have this one feature, which is that the viscosities increase very rapidly. And then you have a transition called the glass transition, where you transform from an amorphous solid, or your liquid is frozen in a disordered structure, but in a solid state. And one tries to attempt understanding the dynamics by looking at how you make transitions between local minima in a rugged energy landscape. Okay, so the behavior of the Pearson model has been used to suggest a framework in which to understand the nature of the glass transition. But a spin model is not a model of a liquid. So more recent work of Parisi and co-workers have actually attempted to develop a theory of the glass transition using these ideas in fluids of hard particles, but equivalently to what was done with the spin glass model, or somewhat similarly to what has been done in the spin glass model. It turns out that you can do sort of satisfactory calculations in the limit of infinite spatial dimensions. So you have a mean field theory of the glass transition of hard particle systems by taking this limit of infinite dimensions. And so there is more interesting stuff that comes out, because so far I described to you two kinds of spin glass transition, a first order transition and a continuous transition. So what happens in this particular theory is you first have a first order transition, which is like a normal glass transition. But if you imagine that you're in one of the free energy minima corresponding to one of the glasses, then there is a second transition, which is of continuous nature. It's called the Gardner Transition, after Elizabeth Gardner, who did this work before she sort of died of cancer at a very early age, cutting short a very promising career. So there is sort of this curious mix of first order, random first order and continuous phase transitions. There are interesting connections to the physics of jamming, but I will not have time to talk about that. Let me spend about 5 minutes just to go through very quickly at some of the ramifications. Like I said earlier, the Parisi solution to the spin glass problem provided a very specific and detailed picture of what happens in one glassy system, based on which to think about a lot of other things. And here is a list of some key directions in which these ideas have been taken forward. One is modeling associative memory, neural networks, learning algorithms. So that's one class. There's been a lot of work in looking at optimization and computational complexity. There's been work on looking at problems like the protein folding, but I'll mention that specifically, inspired by spin glass ideas. And there's also been a lot of development in computer simulation techniques that have been motivated by this understanding or the picture of glassy states and energy landscapes and how to overcome them. Okay, so I'll just literally take 1 minute in each of these. So associative memory is a form of memory where you recall information from partial cues, and this is something that's a common experience. And so you can imagine that if I have some partial information about something, this is like being close to the full memory in some space, right? And then one key sort of feature to take away from our understanding of spin glasses is that there can be many different attractors, many different local minima. And therefore, depending on where I start from, I can go to different minima, which are the full memories. And this is the basis of what's called the Hopfield model, which is described in terms of an energy function, which looks exactly like what I wrote earlier, except the interaction. So you sort of start backwards. You say, first, I have a particular spin configuration, which is my memory, and I want to define an energy function that remembers this pattern. And the way you do it is to pick the interaction strengths Jij to correspond to the particular pattern that you want to remember, or in the case of multiple patterns, as a sum over the patterns that you want to remember. It's called the Hebbian Rule. And there's a very interesting work using spin glass theory, answering questions like how many memories can be stored reliably. And this work has been extremely productive, lots of work using spin glass ideas and methods and neural networks, learning algorithms, machine learning, etc. A related class in some sense of problems is looking at optimization problems. One specific example I'll mention, to which Giorgio Parisi made a significant contribution himself, is called the satisfiability problem. So basically the idea is if I have some n logical variables and I construct logical propositions or clauses involving k variables, how many such clauses can I satisfy simultaneously? Okay, and this problem has analogies with the glass problem, and this has been investigated, and it has been demonstrated that there is a critical number of clauses that you can satisfy before you undergo a phase transition where the number of unsatisfied clauses begins to become finite. And so the protein folding problem is that you have proteins which are random heteropolymers, and how such random heteropolymers and under what conditions do they find themselves in the native structure. And this has been investigated using spin glass language, and there is sort of the proposal of what's called the principle of minimum frustration, and also a folding funnel energy landscape for proteins as conditions to be met in order to have good folders. And finally, a variety of techniques, including some to which Parisi contributed personally, for simulating effectively systems which display complex energy landscapes. All of these have been ramifications of the work of Parisi. Let me finally acknowledge numerous publications and sources, especially Wikipedia. What would we do without it? Which haven't been acknowledged specifically in making this talk. Feedback from Chandan Dasgupta and some of my group members. And let me finish by congratulating Parisi for the Nobel Prize in appreciation of his wide-ranging contributions to theoretical physics. I indicate some of sort of the key areas to which he has contributed, and it does indeed span a wide range, both in terms of the subjects and the scales and so on. Thank you for your attention. Let me stop there.
Okay, thank you, Srikanth, for the very nice talk. Now we'll invite questions. You can just write down the questions in the chat box. Okay, let me check how many questions we have. Okay, there is a questions by Shiladitya Sen Gupta. Is ultrametricity is experimentally demonstrated?
Good question. I am told that, this is something that I'm not familiar with, but this did come up in another talk that I heard, that there have been sort of some recent work involving lasers, where apparently they have experimental evidence or realization of replica symmetry breaking, but whether ultrametricity per se has been experimentally demonstrated, I'm not sure, because it's sort of a microscopic property which involves overlap between different frozen states. But it certainly has been looked at and demonstrated in simulations.
Okay, there are two questions by Professor Shobana Narasimhan. The first question is there any connections at all between the work of the two Japanese laureates and that of the Parisi, apart from the fact that they all deal with complexity?
So no connection to what I believe Parisi was recognized primarily for, but it turns out that one of the significant works of Giorgio Parisi is a model for climate change, which it sort of involves very long time behavior of why the mean temperatures can vary, between ice ages and non-ice ages, and apparently whatever astronomical variation that you have on the timescales of tens of thousands of years is not sufficient to explain the strong changes in temperature. And but Parisi and co-workers looked at a phenomenon called stochastic resonance, which will lead to such large changes in the presence of small perturbations. And so there is some connection to work that Parisi did on climate change, but it's, I think, like this slide shows, he's also done work on turbulence and multifractal spectra of turbulence and so on. So he certainly contributed to problems that are related to what the other gentleman got the Nobel Prize for. But this work per se, the connection is not very strong. So in terms of the work on glasses, the connection is not very strong, but there is sort of an underlying theme of how to understand the consequences of fluctuations and disorder in both. But I think it's sort of a Nobel Prize for a broad area where two dominant themes have been picked out.
Yeah. And the second question by Professor Shobana is, was Giorgio Parisi awarded the Nobel Prize for a specific discovery, a method, or a body of work?
Well, I don't know. If you look at the citation, it's sort of phrased as being about a body of work, but it also mentions specifically disorder and fluctuations. So I mean, if you ask me, so the work that I described, specifically the work on spin glasses, is a key piece of work for which he should be recognized by itself. but he's certainly done a whole lot more.
Yeah, but if you see the H index of Parisi, it is very, very high.
Yes, no, that's what I'm saying. So his actually most cited work is in quantum chromodynamics before he started to look at spin glasses and on asymptotic freedom. But he's done work on spin glasses. Another highly cited work of his is something called the Gardner Parisi Zhang model for the growth of interfaces. He's done work on turbulence. He's done work on climate change. So yeah, I mean, he has made a lot of very important contributions in a whole range of topics. But yeah, like I said, if I look at his work in spin glasses, I believe that by itself deserves the Nobel Prize, regardless of all the other things he's done.
Another question by Professor Bandana. Can you elaborate a bit more on how spin glass relates to the neural network?
Do you want me to? Because I think, I mean, let me just go back to the Hopfield model, right? I mean, basically, if you if you look at sort of if you look at okay, so I didn't say anything about neural networks as in the brain and artificial neural networks. So there, what you have is a bunch of neurons which are connected by synapses, right? So there's some interaction between them, which determines the overall state, and the interactions are what get modified through your experience, right? So these are like the couplings that you have, this JIJs, and as a result of these interactions between the neurons, either artificial or biological, you then have a certain state that the overall network can be in. And or even if you start out with some trigger, you go towards a state of the neural network, and that's equivalent to a certain spin configuration, right? So the network of interactions in the Hopfield model and other models of its kind are like the interactions between neurons, and the particular memories are represented by the state of the neurons. Yeah, I don't know how much more I can say, but so it's sort of a natural model for how you might store and recall memories. You do that by modifying the interactions between the individual units.
So the next question by Krishna Kanhaiya is asking, will you get a different quantities if we take the ensemble average value of a quantity, and that by using the replica method?
Well, you're always doing an ensemble average. So when you write down the partition function, that's an ensemble average. Maybe I wasn't very clear about that. But so when you write down the partition function Z, it is an ensemble average. But when you're also averaging over disorder, the question is how you should do it. I went too far. Yeah, so this is an ensemble average for the expression for Z. So you're always doing the ensemble average, but in addition, for disordered system, you also have to do a disordered average. Yeah.
Okay. So next will go to the questions from the YouTube. Questions by Dr. Avinav Pratap Singh. He asks here two questions. The first question is, are there any general features of complex systems that arises out of the Parisi solution?
Well, like I said, one sort of very general feature that we encounter in a variety of what we call complex systems is the presence of multiple local minima of energy or free energy, or in a dynamical description, the presence of multiple attractors. This is clearly what comes out of the Parisi solution, right? So like I said, it's not like people had never sort of talked about or thought about these kind of descriptions. For example, in the case of structural glasses, there has been sort of an appreciation of an energy landscape which is complicated, that contributes to the dynamics, the non-trivial dynamics of class formers, that goes further back in time. But in my opinion, what the spin glass theory does is to provide, like I said, one particular case where you really know a lot about the detailed solution of the problem. And this therefore acts as a sort of a reference point for how you think about a lot of other things.
Okay, his next question is, are people suggesting that entropy goes to zero below TC in entropy vanishing transition?
Yes. So, but it's not the full entropy. The full entropy of any thermodynamic system goes to zero at zero temperature. But the idea is, so in this particular picture for which I didn't spend much time on, so the middle picture in the bottom row depicts what is called the excess entropy, which is the entropy of the liquid minus the entropy of the crystal. And that by extrapolation goes to zero at a finite temperature at the glass transition, what is called the ideal glass transition temperature. But not the full entropy, of course. The full entropy, goes to zero at zero temperature.
Okay, the next question is by Dr. Tapan Naik. Excellent presentations. Could you elucidate how different Parisi's contributions are all theoretically interconnected, from QCD to spin glasses, to climate changes, to bird flocks?
The common element is Parisi. I don't know if there's anything more.
I mean, is there any single equation or something which connects to all?
No, but I'm told that in fact, I did ask somebody, I don't know about the work. I know that he did something that's very important in QCD, but I don't know the details. But apparently there also you have to worry about sort of the stability of solutions with respect to something like the overlap matrix that comes up in the spin glass theory. So there was some connection, but if you look at other work, I don't think that there's any connection between what he did in interface growth with what he did in spin glasses. I think it's just, the connection is Giorgio Parisi.
Okay. Now the next question by Binod Krishnan. Would you please comment upon the relevance to planetary system?
Relevance of the spin
to the planetary system.
Like I mentioned, there is some work using the ideas of stochastic resonance that has been applied to long-term climate change. So that's clearly relevant to the planetary system. But spin glass theory, not directly But just as a a couple of steps away, one of the things that people do worry about in looking at Earth science are phenomena like avalanches, landslides, etc. Phenomena of sort of loss of rigidity in aggregates on different scales, and earthquakes. And these have very close relations to problems that people in glass physics, including Giorgio Parisi, look at in terms of yielding behavior of glasses, what is the nature of that. So yeah, I don't know what the connection between spin glasses and planetary science is, but glassy systems and Earth system problems are related.
Now the next question by Trideep Sadhu is asking, is it possible to measure overlap order parameter in an experiment? Yeah, so yeah, this question was asked already. If it's like a real spin glass system, I don't know how to do it, but there may be usually for some of these things, the pet answer is you could do it in a colloidal system. I mean, in a system where your degrees of freedom are mesoscopic. But offhand, I don't know. I don't know whether it's been done or how it can be done. Because it does need access to properties that you don't normally have access to in an experimental measurement. Wait. Sorry, there's a very interesting answer to this, which I almost. So there's one of the places where the overlap function or related quantities comes up is looking at aging behavior. Okay, and basically, if you look at sort of a fluctuation dissipation measurements, the nature of the relationship between, so normally in the fluctuation dissipation relationship, the slope of a plot of one versus the other is the inverse temperature. But in aging systems, there is a lot of theoretical work which indicates that these are connected to the overlap function in some indirect way. And this has actually been definitely measured in simulations. And I'm reasonably sure that it has been measured experimentally, but I'm not 100% sure. But it can easily be done. So I take back what I said. I think it can be measured experimentally. And it probably has been, but off the top of my head, I don't know who and what. Okay, there is actually not a question, there is a comments by Dr. Ramani Gupta about all the works of Parisi. She has commented that theoretically it is actually universal behavior of complex objects, all in QCD or spin glasses or climate changes or bar flocks. So I think this is all questions. So thank you again, Srikanth, for these nice talks. Yeah, thank you. It's been my pleasure. But
yeah,
anything to get? Yes.
Yes, thanks, Srikanth, for really a very nice talk, because it was a complex subject and you made it really very interesting and understandable. Thank you, Bibas and Punjab University for hosting this talk. And thanks to all the audience, both from Zoom and YouTube. And IPA has a few more events in November, so please visit the webpage for further events. On 24th November, we have Hema Ramchandran Memorial Lecture by Dr. Ravi Gopal Verma, neurosurgeon, and he will talk about brain-computer interface. So see you all there. Thanks once again to all of you.
Thank you.
Let me stop the streaming. Yeah.